This presentation covers the Multicast DNS protocol, otherwise known as mDNS. The Internet Engineering Task Force defines Multicast DNS as a protocol that's aimed at helping with name resolution for smaller networks. It works differently than conventional DNS in that instead of querying a physical name server, all the participants that are on the local network become the name server. Each one has their own name server. Each one is a responder and a querier. Just a few important terms to get straight before moving on is that the host name, when we talk about hosts or nodes, we are referring to fully qualified domain names that have an IPv4 or IPv6 address record. And there are shared resource records where you have many responders that have the same name, resource record type, and class, and unique resource record sets, which are where the sets have the same name, resource record type, and class, but are controller owned by a single responder. Multicast DNS has only one single top-level domain, that is .local. Only host names that end in .local are responsible for multicast DNS. So this significantly limits name resolution traffic on the local network. Host names with other top-level domains, such as you see in the slide here, the .com, the .gov, the .edu, none of those are going to be able to pass on to this network because the protocol demands that for multicast DNS to work, the host has to have a .local fully qualified domain name. Another way that multicast DNS is restricted to local network traffic only is that it utilizes the Class D IP address range that has been specifically reserved by IANA, and that is the range of 224.0.0.0 to 239.0.0.0. As an example of how multicast DNS works, assume that we have three nodes, A, B, and C. Node A would like to use the printing service that node B has. All the nodes in the system function as a server or a client. Node A needs to get the IP address of node B so that it can access that printer. There's no centralized DNS server in this network because it's multicast DNS. So node A right now does not know from where to get the IP address of node B. So in this scenario, node A starts off by sending a multicast query asking for the IP address of the domain name that has the printer on it. And for this case, we'll call that node b.local. So it sends a query asking for that domain name to all the nodes connected to this local network. And consequently, both node B that has the printer on it and node C on this network, they receive the query and decide whether to respond to it or not. And since node B has the authority for this query, and it has that authority since the printer service is located there, it generates a response to answer the question to the query. So in this case, node B is acting as a server for the requested query. The response from node B is multicasted to all the nodes on the network. Node A receives that multicast message and now can use it for accessing the printing service on node B. Before moving on to anything else, I should have brought this up earlier, but this is what the format of what the fully qualified domain name looks like. Multicast DNS names have a fully qualified domain name of the name, hostname dot local. So mycomputer.local. And the specific multicast address for IPv4 is 224.0.0.251. And for IPv6, it's FF02::FB. And here is just an example of the query packet structure. Multicast DNS packet structure follows the same format as a unicast DNS query packet, with the exception of the query's subfields. So you have the transaction ID, the various flags, the count, what I call the count section. This is where you actually see the number of records that the packet has, or you should be expecting to see. And then you have the queries section, and then you have the authoritative name server section. And then this is the data breakdown structure of a response packet. Again, it's pretty much structured the same as the DNS packet structure, with just a few exceptions. Something to note with regard to the query identifier, the query ID, is that that ID must match the ID from the query message. Next are the flags, and these are specific to the response packet. Some of them are very similar to the query packet. Just like the query packet, the response packet also has a section where it does a count of the records that have been transmitted, so you have an idea of what you should be expecting to see in the packet. And then you have the answers section and additional records. And the additional records section is the actual data payload and can be significantly large. I pulled an example of a query packet from the data I captured off my home network using Wireshark. I took a query and the paired response to show you here. So what you're seeing here are the details of the query packet, and you can see by the example that's highlighted that you can see where the various pieces fit into the query packet structure. And then you have the response packet structure. And this is the response packet. And again, you can see the detail of the packet, and you can see where the various sections match up to the packet structure. Responders also have guidelines, and if the responder gets a query for a record that doesn't exist, the response is going to include an NSEC record in the additional record section to indicate that. Second, responders handle query messages that have more than one question by delaying the responses to the queries at random intervals in the range of 20 to 120 milliseconds, or 400 to 500 milliseconds if the truncated bit is set, the TC bit. Responders should aggregate as many responses as possible into a single multicast DNS response message, even if it means that the various responses have to be delayed so that they can be included into the single DNS message. So the packets will actually all wait until the packet is full enough to send. When a responder sends a message with an A record, so that would be an IPv4 format, It will also include the IPv6 version of that record, and it'll put it in the additional section if there's space for it, and then vice versa. A responder sends a response message containing its own address records, and it must include all the addresses that are valid on that interface that is sending the message. And it should not include invalid addresses. There's a special grouping for values that are set for packets that contain resource record information. This is information that is placed in the answer section of the response packet. So you have the resource record name, the type, cache flush bit, which is the Boolean flag that indicates where outdated cached records should be purged, the resource record class, the time to live in which the resource record should be cached, the resource record length in octets, and the resource data type. Probing is the process of when a new device is trying to become aware on the network. So whenever a responder starts up or wakes up from sleep or something new has been connected to the network, the probing process needs to happen. The ability to place more than one question in a multicast DNS query is useful in this situation because it allows a host to use a single message to probe for all of its records. It waits to send that probe for a random number of milliseconds. And that is done to guard against the situation where several devices might all be powered on at the same time. Then you don't have everybody on the network all at the same time. So 250 milliseconds after the first query, the host should send a second, and then 250 milliseconds after that, a third one. If 250 milliseconds after the third probe, there's no conflicting multicast DNS responses being received, the host may move to the next step, which is announcing. If 15 conflicts occur within any 10-second period, then the host must wait at least 5 seconds before each successive additional probe attempt. To be lexigraphically later means that the two competing hosts for the name are compared. They're compared by the record class, the type, and the raw binary content of the R data. Bytes of the raw uncompressed data are then compared, and the bytes are interpreted as 8-bit unsigned values until a byte is found where the value is greater than that of the other one. The last option, if everything else matches up, the very last thing that differentiates them are that the resource record, whichever one doesn't run out of our data, is the one that is deemed lexigraphically later. So for example, if I have a printer called myprinter.local and there are two myprinter.locals trying to vie for that name, and they're both A records, and they both start with IPs of 169.254, then it goes to the third octet. And if the third octet is a higher number than the third octet of the other record, then the larger one is the lexigraphically later host and gets to keep that name. And once that probing part is done, then announcing happens. And the responder must send an unsolicited response containing, in the answer section, all of its newly registered resource records, both shared records and unique records that have been completed during the probing step. If there are too many resource records to fit in the packet, multiple packets can be used. And at any time, if the R data of any of the hosts records changes, the host must repeat the announcing step. In the case of shared records, a host must send a goodbye announcement with a resource record time to live number of 0 for the old R data. And that's going to cause it to be deleted from the data to be deleted from the peer caches before announcing the new data. Should a host witness another host announce an address record with the same name but a different IP address, then that is considered inconsistent, and that address record would be considered to be in conflict. Whenever a responder receives a packet containing a conflicting resource record, the responder must immediately reset its conflicted unique record to a probing state. It must go back to probing and go through those startup steps again. The message sizes for multicast DNS are as follows. You have the IP header, which has 20 bits for IPv4, 40 for IPv6. The UDP header is going to have 8 bytes. And the packet size as a whole can have up to 9,000 bytes, but 1,500 are recommended according to the protocol. But one of the things that can be said about it is that IPv4 and IPv6 are not aware of each other's traffic. They are basically in 2 unrelated local zones. And there can be a host that can participate in both of those zones. They're going to register names and perform lookups using both IPv4 and IPv6, and that enables it to reach and be reached by both IPv4 only and IPv6 only hosts. Some of the considerations for security include the situation where clients cannot be sure that there are no antagonist hosts on the same physical link. To mitigate that, participants need to use IPsec signatures or DNSSEC signatures so that the multicast DNS messages can be distinguished between trusted and untrusted participants. If DNS queries for global names are sent to the multicast DNS address, particularly during a network outage where communication has been stopped with the internet, they can't get out onto the internet, it's especially important to use DNSSEC because the user may have the impression that he or she is communicating with some authentic host when in fact they may really be communicating with a masquerading or a spoofed computer or spoofed host. And the trailing dot at the end of the FQDN is a problem. It's often missed, and when that happens, it changes the domain name to be something of more a relative format. IANA has put in its own requirements into the protocol, and that is that the UDP port 5353 is used for the multicast DNS protocol. It's allocated the IPv4 local multicast address to be 224.0.0.251, and the IPv multicast address to be FF0X::FB, where the X indicates any hexadecimal digit between 1 and F. It also has identified specific DNS records, and it has noted that classes in the range of 32,768 to 65,535 to be incompatible with multicast DNS. IANA also has recorded this list of domains as being special use domain names for multicast DNS. I thought I would wrap up the presentation by reviewing the similarities and differences between conventional DNS and multicast DNS.